students, welcome back. Coming to the next subject, that is a theory of computations. So what is the theory of computation? Actually, everyone is having some idea that theory of computation is somewhat a boring subject when compared to the other subjects in the computer science, but not like that. It is also an interesting and a scoring subject. So let me tell you the introduction part of this theory of computation in this video. So what is a theory of computation? A theory of computation is nothing but it is a branch of computer science that deals with. So the theory of computation is deals with how efficiently a problem can be solved on a model of computation using an algorithm. So this is important. So using an algorithms, we are going to solve problems. Okay, so a theory of computation is a branch of computer science that is going to deal with how efficiently a problem, whatever the problem that occurs in the computer science, if you're dealing with, so how efficiently the problem can be solved on a model of computation using an algorithm. So actually, the theory of computation, a field divided into three main branches. Okay, so theory of computation's field is mainly divided into three branches. So what are this? One is automata theory and language, and another branch is computability theory, and next complexity theory. So the complete subject is going to deal with this. The theory of computation divided into three branches. One is the automata theory and languages, and second is computability theory, and the third one is the complexity theory. Okay, so whenever there are a problem can be solved on a model of computation on a problem use of one is automata theory and languages, and second is computability theory, and the third one is the complexity theory. Okay, so whenever anyone is asked what is the theory of computation, you need to tell that it is going to deal with how efficiently a problem can be solved in a model of computations using an algorithm. So the theory of computation is divided into mainly three branches: automata theory and language, computability theory, and complexity theory. So let me give an introduction, means overview of this three branches. So whatever I said: automata theory or and language. So what is this automata theory and language? This automata theory and language deals with the definition and properties of various mathematical models, various mathematical model of computers. Okay, so what is this automata theory? This automata theory and languages are going to deal with the definition and properties. So whatever the definition means, how the problem is going to be defined and what happened. So it deals with the definition and what are the properties of various mathematical problem models of computation. So what are the different models of mathematical models of computation? That is, examples for this is finite automata, context-free grammar, and Turing machine. So these you call it as a mathematical models of computer. So this automata theory and language is going to deal with the definition and properties of these models, Okay, and next one is, so what is the next branch in this theory of computation? That is a computability theory. So what it is, what does computability theory deals? It deals with what can and what cannot be computed by the model. That's why we call it as a computability theory. What it is going to do, it is going to deal with what we can and what cannot be computed by the model. And another model is, another branch of that deals with the theory of computation, that is complexity theory. So this complexity theory, it groups the computable problems. So whatever the problems that are occur in this mathematical problem, so this complexity theory groups the computable problems based on their hardness. Means all, suppose if it is a large problem out there, then that will be grouped into one category, and if it is somewhat complexity is increasing, means those problems will be grouped into one category. So the complexity theory is going to do, it is deals with a group of computable problems based on their hardness. Okay, so the theory of computation the field divided into these three main branches: automata theory and language, computability theory, and complexity of theory. Actually, what is the main purpose of using this theory of computation? Let me write the main purpose of theory of computation. So the main purpose of theory of computation is it develop formulae mathematical model. It develops a formal mathematical model of computation that reflects real world computers. That reflect real world computers. Okay, did you understand it? The main purpose of using the theory of computation is it is going to develop the formal mathematical models of computation that are going to reflect the real world computers. So this is an introduction part of the Hi students, welcome back. Now let's see the basic call it as a symbols. So whenever you have seen a letter in the theory of computations, okay? So first thing is the basic definition that you have to know is symbol. So we use the term symbol in the theory of computation. So what this symbol indicates? A symbol here is nothing but it is a character. Symbol is a character. Okay, so what is this characters? A characters are nothing but example A, B, C up to Z. So each letter you call it as a symbol. Each character you call it as a symbol. Or even not only the alphabets, the numbers also, numeric values up to 9 is also a symbol. 0 is a symbol, 2 is a symbol, 8 is a symbol, 7 is a symbol. And even the special characters like plus, minus, modulo, okay, you call it as a special characters. These are also you call it as a symbols. So whenever you have seen a letter, a character or a number or a special character, then you call it as a symbol, not an alphabet, not a number. Okay, so in the theory of computation, you call symbol is a character. So whenever you're seeing the character, you have to call it as a symbol. Now coming to the next definition. Next is the alphabet. So you'll get a doubt. Here, these are the alphabets. Again, what is this alphabet? I'm saying here the alphabet is a symbol. Okay, but I'm taking another definition, alphabet. Okay, so there is no confusion. A set of characters, you call it as an alphabet. Set of characters, not a single one. Set of characters, you call it as an alphabet. Okay, let me write. An alphabet is a finite, non-empty set. Remember that. Means something has to be there, which should not be non-empty set. Of non-empty set of symbol. A non-empty set of a symbol, you call it as a finite. You call it as an alphabet. So an alphabet is a finite, non-empty set of a symbol, and it is denoted by, sigma. It is denoted by sigma. Let me take the example. Suppose sigma. Whenever you are seeing the sigma in this theory of computation, you have to call it as an alphabet. A sigma is set of finite, non-empty set. 0, 1. It's a set. The set can be represented with open parenthesis and the closed bracket. Sigma is a set of a symbol, you call it as a finite. You call it as an alphabet. So an alphabet is a finite, non-empty set of a symbol, and it is denoted by, sigma. It is denoted by sigma. Let me take the example. Suppose sigma. Whenever you are seeing the sigma in this theory of computation, you have to call it as an alphabet. A sigma is set of finite, non-empty set. 0, 1. It's a set. The set can be represented with open parenthesis and the closed brackets. Okay. So this is set of, you call it as a binary alphabets. So what are the binary alphabets? The binary alphabets are nothing but 1 and 0, so the binary numbers. So if it is a set of binary alphabets, you call it as an alphabet. And sigma is equal to, let's take A, B up to Z. This is set of all lowercase letters. So you have to remember that the alphabet is denoted with sigma. Whenever the sigma is there, a set should be there. It should be a non-empty set. Means you have to include any single character in the set. And another example, let me take the special characters also. These are all the set of all special characters. Special characters. So I hope you understand what is the definition of the alphabet. So the basic definition. Here each character you call it as a symbol, and the set of those symbols you call it as an alphabet. And next definition, come to the next definition. That is a string or a word. Even you call it as a string, or simply you can call it as a word also. A string is a finite. Set sequence of symbols. Remember this. A sequence of symbols chosen from some alphabets. From some alphabets means either you can choose them from this, or you can choose them from this, or choose them from this. From some alphabet. Let me take example. Here, let me take the example. Let's take a set of a string is a finite sequence of symbols. Here, I'm taking a sequence of symbols like 0 is a symbol, 1 is a symbol, 1 is a symbol, 0, 0. So what do you call this? So it is a string. You call this complete as a string, or you can call it as a word. String or a word from binary alphabet of set sigma is equal to 0, 1. Right? Is it correct? I have taken I have implemented this word or a string by taking the alphabet of set 0, 1. So a string is a finite set sequence of symbols chosen from alphabets. I have to choose them from this alphabet. That is I have chosen this word from this alphabet. That is 0, 1. I have written like 0, 1, 1, 1, 0, 0, 1, 1, 0 like this. Okay. Let me take another example so that you understand what this word from this alphabet. That is 0, 1. I have written like 0, 1, 1, 1, 0, 0, 1, 1, 0 like this. Okay. Let me take another example so that you understand what exactly the string or a word is. And I'm saying it is taken from the set of alphabets. Let me take A, B, B, A, C, A, B. So I call it as a string. It is a string, or you can call it as a word. So I have taken this string from alphabet set. What I have taken? So here A is there, B is there, C is there. Only 3 letters are there. So I have taken from these 3 letters. A string from the alphabet of set sigma is equal to A, B, C. So from these 3 characters, I have implemented this word. So that is a string. A string or a word, you call it as it is a finite set sequence of symbols chosen from some alphabet. So don't confuse. Each letter in this alphabet is a character, or you call it as a symbol. And set of that symbols, you call it as an alphabet. In this alphabet, we are developing a string or a word. Okay. First symbol 2. Alphabet. From the set of alphabets, we are writing a string or word. So I hope you understand what exactly the symbol is.
symbols are nothing but the letters A or 1 or 0 like that, and alphabets is set of strings or set of alphabets, and a word is a simple word taken from set of alphabets. So like this. Okay, I have taken this from the set A, B, C, D. Thank you. Hi students, let's continue with the basic definitions on the theory of computations. So far we have seen about what is an alphabet, what is a string, and what is a symbol. Now let's see the empty string. The continuation of that video. That is the next is empty string. So what do you call this empty string? The empty string is a string. The empty string is the string with a zero occurrence, with zero occurrences of symbols. That is a no symbol. You can simply call it as a no symbols also. And it is denoted by epsilon. So epsilon is nothing but that's a no symbols. Means the string is empty. Okay, the string is empty. You call it as epsilon. You can represent it as epsilon. And next, let me tell you the length of string. Length of string. So length of string, what it is? It is the length of string is the number of symbols. Remember that. Number of symbols in the string. So if you take any string, means it's a set of alphabets. If you take any string, so there you have to count how many symbols are present. That is how many characters are present in that string. It is the number of symbols in the string, and it is denoted by mod W. So why I have taken W string, or you can call it as a word also. Okay, so the length of the word, the length of the string is denoted by mod W. So let me write the example for this so that you can understand. What is this length of the string. Example, let me take a word or a string like 0 1 0 1 1 0 1 0. So from where I have taken this, remember that whenever you have written a word or a string, you have to write from where you have taken that word. So I have taken from binary alphabet. I have taken from binary alphabet. The alphabet is represented as sigma. Binary alphabet means 0, 1. So from this set 0, 1, I have taken this word. Okay, don't forget to write. Whenever you're writing a word, you have to write from where you're getting that word. From binary alphabet, sigma is equal to 0, 1. Okay, so now I have to.
Hi students, welcome back. Now let's see the basic definitions or the basic terminologies that that in the theory of computation. So if you know these basic definitions, then you can easily understand what are the problems that are going to be solved.
Calculate the length of the string. So what is this length of string? Length of string mod W means I have to count how many characters or the symbols that are present in the string. 1 2 3 4 5 6 7 8 9. Okay, so the length of the string is 9. So did you understand how I had done this? So just take a word or a string from any of the set of the alphabet, and then you need to calculate the length. And one more string. So you have seen the length of the string. That is a mod W is the length of the string. You have to count number of characters or the symbols in that string. Concatenate means join two or more strings. Joining two or more strings side by side, that you call it as a concatenation of string. So what is this? So let's take let x is equal to a1, a2, a3 up to an. And I have taken another letter y is equal to b1, b2, b3, so on up to bn. Now I want to concatenate strings. Concatenation of string xy. Concatenation means I'm just combining these two strings like first a1, a2, a3 up to an and b1, b2, b3 up to bn. So this is how you're going to concatenate. A side by side. Let me take the example. Let's take a string or a word a b a b a, and I have taken another word t is equal to c d c d d c. Okay, now I'm concatenating s definition of string. Hi students, let's continue with the basic definitions on the theory of computations. So far we have seen about what is an alphabet, what is a string, and what is a symbol. Now let's see the empty string. Hi students, let's continue with the basic definitions and theory of computation. So far we have seen so many definitions that the terminologies that we are going to use in the theory of computations. Now let's see what is the power of an alphabet. So you know that the power of alphabet is represented with a sigma. Okay, a sigma here is nothing but it's a set of symbols. So then what is this power of alphabet? A power of alphabet means if sigma is an alphabet, we can express the set of all strings of certain length. We have to take of certain length from that alphabet, means in that set alphabet, by using exponential notation. So we are talking about the power, so that we have to represent that using the exponential notation. So it is denoted by actually sigma is an alphabet, then power of an alphabet is represented by sigma power k. So this sigma power k is the set of strings, of length k, means some set of strings will be there. So for that you need to calculate the length of that, and that length should be represented as exponential. Sigma power k. K is the set of strings of length k. Okay, each of which symbol is in sigma. So let me explain you with an example so that you clearly understand what is the power of an alphabet. Okay, sometimes if you didn't understand the definition, no problem. If you see the examples twice or two or more examples, then you can easily understand and you can easily frame the definition also. So let me take, I said clearly understand what is the power of an alphabet. Okay, sometimes if you didn't understand the definition, no problem. If you see the examples twice or two or more examples, then you can easily, so symbols, two symbols. If I take the power of, so equal to 1 means how many symbols? 2 symbols are there. 2 power 1 is equal to 2. So only 2 symbols. Suppose if I take sigma square, sigma power 2, exponential 2, means I have taken k is equal to 2. K is equal to 2 means you'll get 0, 0, 0, 1, 1, 0, 1, 1. So therefore, 2 square is equal to 4. So the binary symbols are 0, either 1. But here the k is, I have taken it as a 2. 2 means 2 square is equal to 4. 4 strings we have to get. 0, 0, 0, 1, 1, 0, 1, 1. Let me take one more example. So in this example, I'm taking sigma power 3. That's sigma cube. So here I get the strings as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So totally 1, 2, 3, 4, 5, 6, 7, 8. Therefore, 2 cube is equal to 8. Okay. So here the sigma is, I'm taking the binary values of alphabet set 0, 1. Clean closure. Two cube is equal to 8. Okay. So here the sigma is, I'm taking the binary values of alphabet set 0, 1. So in that you are having 2 symbols. 2 power 1 means 2. 2 square means you'll get 4. Sigma cube. 2 cube means you'll get 8. So the set of string over an alphabet, so this is a set of strings. These are all the set of strings. So the set of strings over an alphabet sigma is usually denoted by sigma star. That is a clean closure. We call it as a clean closure. So for instance, we can take closure. We call it as a clean closure. So for instance, we can take it as, let's take sigma star is equal to 0, 1 power star. So what it represents? So the clean closure is a set of empty set. Either it is a set of empty set or 0 or 1 or 0, 0, 0, 1 or 1, 0, 1, 1. Still take. That's the power I have taken it as a star. Okay. So this clean closure, you call it as star as a clean closure. The clean closure is a set of empty set with a set of strings. So these are all the set of strings. So therefore, clean closure is equal to sigma power 0. So sigma power 0 is nothing but it's an empty set. Means epsilon. Union sigma power 1. So this is sigma power 1. And union sigma square. So this is all the sigma square. Union sigma cube. So like that. So with epsilon symbol. So this is clean closure. So the power of symbols can be represented, power of alphabet can be represented as a clean closure. Okay, clean closure is equal to sigma power 0, it's nothing but empty set, union, sigma power 1 is 0, 1, union, sigma square, that is 0, 0, 0, 1, 1, 0, 1, 1, union. So like that it will be up to n numbers. Okay, and the set of strings over an alphabet, let me take another. The set of strings over an alphabet sigma excludes epsilon. So previously I have included the epsilon. So here I'm just excluding the epsilon. Excluding epsilon is usually denoted by sigma power, sigma plus. So we call it as a clean plus. So for instance, we can take this as just sigma plus. So So we call it as a clean plus minus epsilon. This is you call it as a clean plus, or you can simply write sigma power plus is equal to sigma power 1. Instead of sigma power 0, you have to start with sigma power 1 because we are excluding this a bit. It is a clean plus. Clean closure means it's a sigma star. Okay, here we are including the epsilon means sorry, it is clean closure. Hi students, welcome back. Let's continue with this theory of computation. We are discussing about the basic terminologies. That is the basic definitions that we are going to use in this theory of computations. Now let's discuss about the languages. Okay, so actually here the language is nothing but it's a finite set. It is a finite set of non-empty strings. Non-empty strings. So you have to remember that if it is empty string, it is nothing expressible. Means it is an epsilon. Nothing is there. Language means there is something should be there. Okay, so at least a character itself you call it as a language also. A character, single character or a symbol or alphabet, anything you call it as a language. But it should be remembered that a finite set. It should be a finite set of non-empty string. Non-empty string. There should be something. If something is there, then you call it as a language, right? So if sigma is an alphabet, let us say if sigma is an alphabet, and that is L. L is a language, right? L is a language, superset of clean closure. Okay, that's a clean closure. Then L is a language. So let me explain one example so that you'll understand what exactly the language is. Example, let's take the set of legal English words. The set of legal English words, you call it as a language, right? And the set of legal C programs also. The set of legal C programs is also you call it as a language. Not only the C, C++, whatever the language. As a set of legal programs, you call it as a language. And the set of string, let me take the set of string consisting of n zeros. Let us take n zeros followed by n ones. So let me take something, means I have taken, it's a finite set of non-empty string. So I have taken epsilon 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, so on. So it's a set of strings consisting of n zeros followed by n ones, means it is following some legal rule. It's a legal rule. So then that you call it as a language. Okay. So it is a finite set of non-empty string. So let me take some operations on languages. Different operations on languages. Operations on languages, right? Let me tell you. The first operation, let us take complementation. First operation is we are performing language. This is followed by n ones. So let me take something, means I have taken, it's a so not a character or a symbol or alphabet, anything you call it as a language. But it should be remembered that a finite set, it should be a finite set, characters, strings, non-empty strings. So you have to remember that if it is empty string, it is nothing expressible, means it is an epsilon, nothing is there. Language means there is something should be there. Okay, so at least a character itself you call it as a language also. A character, single character or a symbol or alphabet, anything you call it as a language. But it should be remembered that a finite set, it should be a finite set of non-empty string. There should be something. If something is there, then you call it as a language, right? So if sigma is an alphabet, let us take if sigma is an alphabet, and that is L. L is a language, right? L is a language, superset of clean closure. Okay, that's a clean closure. Then L is a language. So let me explain one example so that you'll understand what exactly. Also, the set of legal C programs is also you call it as a language. Not only the C, C++, whatever the language. As a set of legal programs, you call it as a language. And the set of I have taken, it's a finite set of non-empty string. So I have taken epsilon 0, 1, 0, 0, 1, 1. Legal some operations on languages. The legal rule. So then that you call it as a languages. Okay. So it is a finite set of non-empty string. So let me take some operations on languages. Different operations on languages. Language. You call it as an complementation of language. So L bar is equal to clean closure minus L. Then you will get the complementation, right? So let me take the another operation on language, that is a union. Union, it's nothing but combination of two languages. Let L1 union. So here L be a language over an alphabet sigma, then the reversal of L is denoted by LR. This is language reversal is WR, where such that W is in language. Next operation that is performed on language is clean closure. So I already discussed about this clean closure. L1 dot L2 or X is in L2. Okay, X such that X is in L1 or L2. Let me sigma. So by using some alphabet sigma, we are constructing one language. Let's take L be a language over an alphabet sigma. Then in this type of symbol L bar, you call it as an complementation of language. So L bar is equal to clean closure minus L. Then you will get the complementation, right? So let me take the another operational language, that is a union. Union, it's nothing but combination of two languages. Let L1 and L2 or language over an alphabet sigma. Then the union of L1 and L2, it's denoted by, so what? It is denoted by L1 union L2. Okay, so this is for complementation and this is operation for union. So here it's a condition. L1 union L2 is X. So if you do this operation, you'll get some string. Okay, so that this X for all X is in L1 or X is in L2. Okay, X such that X is in L1 or L2. So if you perform this operation, you'll get one string. That string is in L1 or L2. Let me take another operation on our language. That is the third one. Let me take intersection. For union. So here it's a condition. L1 union L2 is X. So if you do this operation, you'll get some string. Okay, so that this X for all X is in L1 or X is in L2. Okay, X such that X is in L1 or L2. L2. Okay, so this is for complementation and this is operation for union. So here it's a condition. L1 union L2 is X. So if you do this operation, you'll get some string. Okay, so that this X for all X is in L1 or X is in L2. Okay. Okay, X such that X is in L1 or L2. So if you perform this operation, you'll get one string. That string is in L1 or L2. Let me take another operation on our language. That is the, if you perform this operation, you'll get one string. That string is in L1 or intersection. Okay, so let L1 and L2 be languages over an alphabet sigma. Over an alphabet sigma, then the intersection of or my definition while I'm writing this, let L1 and L2 be language over an alphabet sigma. Then what is a concatenation? L2. So this is about the operation that is performing on language. That is a concatenation. So L1 dot L2. So this is for intersection and this is for concatenation. L1 dot L2 is, you'll get one string W1 dot W2 where W1 is in L1 and W2 is in L2. So this is about the operation that is performing. Then which, let me write language W, did not touch that. W is in R. This is language reversal. Is WR, where such that W is in language. Next operation that is performed on language is clean closure. So I already discussed about this clean closure. Let me write, let L be a language over an alphabet sigma. Then the clean closure of L is denoted by, what is the symbol of this? You already know, L star. Clean closure is, you'll get X for an integer as a condition and greater than or equal to 0. Okay, so let me write the formula for this clean closure. If you take two languages, let me take the language X is equal, clean closure is, you'll get X for an integer as a condition and greater than or equal to 0. Okay, so let me write the formula for this clean closure. If you take two languages, let me take the language L x2. The formula for this clean closure is, positive closure, I. So the example for this is, let me take, if you take the A clean closure, it can be represented as epsilon, because clean closure means it should be included the epsilon empty string. Epsilon A, so like that. Okay, so let me take the another operation on language, that is a positive closure, or you call it as a plus closure, positive closure. So in the positive closure, you have to exclude the epsilon. Let L be a language over an alphabet sigma. Then the closure, okay, then the closure of L is denoted by L plus. Okay, so is X such that for an integer, so here it should be excluded the epsilon. So we have to take n greater than or equal to 1. Then x is equal to x1, x2, so on, xn, and x1, x2, so on, xn, or in language L. So the formula for this is, if we take positive closure on language L is equal to, it is, instead of writing 0, 0 means I0 to infinity is for clean closure, and I is equal to 1 to infinity is the positive closure. Remember this is the main difference between the positive closure and the clean closure. Let me take the example. A plus means here you need to exclude the epsilon. So you have to start with A, so on. Okay, so these are all the different operations that are performing on the language. Thank you. Students, welcome back. Now coming to the next topic in this theory of computation is a finite automata. So here in this video, I want to explain you what is exactly the finite automata with a formal definition. FA, you call it as a finite automata. So the complete subject is depends upon this finite automata. A finite automata is an abstract computing device. It is some abstract computing device. It is a mathematical model of a system with discrete inputs, outputs, states, and set of transitions from state to state that occurs on input symbol from alphabet sigma. So here in the finite automata, you're going here you are having the inputs, outputs, some states, or and the transitions that are going to perform on states from one. Hi students, welcome back. Let's continue with this theory of computation. We are discussing about the basic terminologies, that's the basic definitions that we are going to use in this theory of computations. Now let's discuss about the languages. Okay, so actually here the language is nothing but it's a finite set. It is a finite set of. Students, welcome back. Now coming to the next topic in this theory of computation is a finite automata. So here in this video, I want to explain you what is exactly the finite automata with a formal definition. FA, you call it as a finite automata. So the complete subject is depends upon this finite automata. A finite automata is an abstract computing device. It is some abstract computing device. It is a mathematical model of a system with discrete inputs, outputs, states, and set of transitions So this finite automata can be represented in three models. One is a graphical model, tabular model, and mathematical model. Okay, so remember that the finite automata can be represented either in graphical. Graphical means you can write the transition, you can represent that automata with set of inputs, set of states and outputs, transitions, everything in the form of transition diagram or transition table. Tabular form means transition table. Mathematical means you call it as a transition function or simply a mapping function. Transition function or mapping functions both are the same. So the finite automata can be represented either in graphical, tabular, or transition function. So let me explain you the formal definition. So I said what the finite automata is consisting of set of tuples, set of inputs, outputs, and some things will be there. So that you call it as a tuples. A finite automata is a phi tuple. There are q, sigma, okay, delta, q naught, f. So here q you call it as a finite set called states. So q represents the states. A q in this language you call it as a finite set called the states. And you already know the sigma is nothing but the finite set. It is a finite set called alphabets. Sigma you already seen. Sigma is an alphabet. Q is a set of states. And coming to the delta, delta is nothing but it is a combination of states into alphabets. You will get a q. So q into sigma is the q is a transition function. So remember that this delta you call it as a transition function. Transition function. Q into sigma you'll get implies the next state. A state with the finite input state you will get another state. That is a transition function. And this q naught you call it as a start state, also initial state. So q naught is, remember that it is initial state, or also you call it as a start state. And f you call it as a acceptance state or final state. F is final state. So starts with the q naught and end with the final state f. So these q naught and f will be present in the finite set called the states. These are also called as the states. So remember that the formal definition of finite automata means you have to write this definition. It's just a simple. It consisting of phi tuples. What is that? Sigma is an alphabet, q is a set of states. And coming to the delta, delta is nothing but it is a combination of states into alphabets. You will get a q. So q into sigma is the q is a transition function. So remember that this delta you call it as a transition function. Transition function. Q into sigma you'll get implies the next state. A state with the finite input state you will get another state. That is a transition function. And this q naught you call it as a start state, also initial state. So q naught is, remember that it is initial state, or also you call it as a start state. And f you call it as a acceptance state or final state. F is final state. So starts with the q naught and end with the final state f. So these q naught and f will be present in the finite set called the states. These are also called as the states. So remember that the formal definition of finite state or state. So transition function. Q into sigma you'll get implies the next state. A state with the finite input state you will get another state. That is a transition function. And this q naught you call it as a start state, also initial state. So q naught is, remember that it you will get another state. That is a transition function. And this q naught you call it as a start state, also initial state. So q naught is, remember that it is initial state, or also you call it as a start state. And f you call it as an acceptance state or final state. F is final state. So starts with the Q naught and end with the final state F. So these Q naught and F will be present in the finite set called the states. These are also called as the states. So remember that the formal definition of finite automata means you have to write this definition. It's just a simple. It consisting of 5 tuples. What is that? Q consisting of finite set states. Sigma is a set of alphabets, and delta is a transition function. Q naught is the initial state, and F naught is the final state. That's it. A finite automata is a 5 tuple. There, M is equal to Q sigma delta Q naught F. So I hope you understand what exactly the finite automata is. Thank you. Students, welcome back. Let's continue with this finite automata. So I said the finite automata can be represented in the graphical, tabular, and mathematical. So the Students, welcome back. Now coming to the next topic in this theory of computation is the finite automata. So here in this video, I want to explain you what is exactly the finite automata with a formal definition. FA, you call it as a finite automata. So the complete Students, welcome back. Let's continue with this finite automata. So I said the finite automata can be represented in the graphical, tabular, and mathematical. So the graphical is nothing but a transition diagram. Tabular is a transition table. Mathematical is a transition function. Okay. So these will be included in the finite automata. So before entering into the subject or in the we discussed about the different languages. So get a clear idea what is this transition diagram, transition table, and the transition function. So in this video, I want to explain you what is the transition diagram and the transition table. So with the help of a it's an example, I'll explain the diagram and the table. So first let's see the transition diagram. So this diagram you also call it as a graph. It is a directed graph. Directed means it should be pointing to some state. Okay, a graph that is pointing to some state, you call it as a directed graph. So it is a directed graph associated with the vertices of the graph corresponds to the state of a finite automata. So let's take a finite automata. So here you are having 3 states. What are the 3 states? Q0, Q1, Q2. So these are all the 3 states that are present. And the starting state is the Q0 is the initial state and Q2 is the final state. So whenever the final state is there, you have to represent it with the 2 circles. So this represents the final state. This is the indication of the final state, or you call it as an accepting state. So Q0 is the initial state and Q2 is the final state. Whatever the states that are present in between the start and the final, initial and the final, those states you call it as an intermediate state. And here there are 2 inputs we are taken, 0, 1. So 0 is a 1 input and 1 is another input. Okay, so it is a directed graph. Directed means it should be pointing to some state. Okay, a graph that is pointing to some state, you call it as a directed graph. So it is a directed graph associated with the vertices of the graph corresponds to the state of a finite automata. So let's take a finite automata. So here you are having 3 states. What are the 3 states? Q0, Q1, Q2. So these are all the three states that are present. And the starting state is the Q0 is the initial state and Q2 is the final state. So whenever the final state is there, you have to represent it with the two circles. So this represents the final state. This is the indication of the final state, or you call it as an accepting state. So Q0 is the initial state and Q2 is the final state. Whatever the states that are present in between the start and the final, initial and the final, those states you call it as an intermediate state. And here there are two inputs we are taken, 0, 1. So 0 is a one input and 0, 1 is another input. Okay, so initial state, final state, intermediate state, and this should be represented with a directed graph holding the inputs. Now let's see the transition table. And this should be represented with the initial state, final state, intermediate state, and this should a transition table here. It is basically a tabular representation. Table itself, we know that we have to represent it in the form of a rows and the columns, right? It's a tabular representation of the transition function that takes two arguments, that is a state and a symbol. We are taking a state and a symbol. State means either initial state, intermediate state for final states. And the symbols are nothing but the input symbols. Here in this previous example, the 0 and 1 are the symbols. And the return value is nothing but the next value. That is a transition function, you know that. Delta is equal to, Q into sigma, you'll get the Q. Okay, initial state, some state, not initial state, symbol, you'll get the next state. So that you have to know. Now let's see the transition table. The transition table consisting of the rows corresponds to the states. The rows are represented with the states. Okay, so the rows are represented with the states. And the columns are represented with the input symbols. Input symbols. There is 0 or 1 or whatever, A, B, alphabets. So set of strings, so set of symbols. That is the alphabet. So rows represents the states and columns represents the input symbols, and entire corresponds to the entries. So whatever the entries that are present, entries, these entries represents the next state. Remember that whenever you are writing the table, The rows represents the states, column represents the input symbols, and the entries in that state should be the next state. The start state is marked with an arrow. Okay, so start state always marked with, suppose this is a start state, you have to mark it with arrow. And acceptance state, the final state should be marked with star. Remember that. These are the points that you have to remember while you're implementing the table. Okay, so let me show you how to draw the table. Let me take this transition diagram. By seeing the diagram, I have to draw the table. Okay, so let me show you how to draw the table. Let me take this transition diagram. By seeing the diagram, I have to draw the table. So Q0, Q1. These are the two states. So Q0 is the initial state, and here I have taken only two states, and Q1 is the final state. So the final state always represents with two circles. Okay. And the Q0, here in the rows you need to write the states, Q0 and Q1. And in the columns you have to write the input symbol, 0 and 1 are the input symbol. And the entry should be the next state. So now see, Q0 to 0, Q0 to 0. What is the next state? If Q0 to the 0, it goes to the next state. What is the next state? Q0 itself. So write Q0 here. Next, Q0 on 1. Q0 on 1. It goes to which state? It goes to Q1 state. So write Q1 in the entry. Now coming to the Q1. So Q1 on 0 goes to Q1 only, right? And Q1 on 1 goes to Q1 only. Okay, so this is how you have to write the transition table by seeing the transition diagram. Now let me explain you the transition function. A transition function here, the mapping functions or the transition function is denoted by delta. Remember that. The mapping function or transition functions are denoted by delta. Here the two parameters are passed to the transition function. One is the current state and the input symbol. So this is the current state and this is the input symbol. You will get the next state, right? The transition function is always returns a state which can be called as a next state. So this is the formula. The transition function is always returns a state and the input symbol. So this is the current state and this is the input symbol. You will get the next state, right? Here the two parameters are passed to the transition function. One is the current state and the input symbol. So this is the current state and this is the input symbol. You will get the next state, right? The transition function is always returns a state which can be called as a next state. So this is the formula. A delta is equal to the current state, comma, the current input symbol is equal to, you'll get the next state, that is Q, it's a current state, into sigma, that is the input symbol, which yields to the next state in the Q. Let me take the example. Suppose delta Q0 comma A. This is a Q0 is the current state and A is the input symbol on that state. It's going to the Q1. It's pointing to the next state Q1. And same with Q0 1, it's pointing to the Q1. So whatever the previous diagram I had taken. So this is about this transition diagram, transition table, and transition function. Remember that. Students, welcome back. Let me continue with the subject. Students, welcome back. Let's continue with this finite automator. So I said the finite automator can be represented in the graphical, tabular, and mathematical. So the graphical is nothing but a transition diagram. Tabular is a transition table. Mathematical is a transition function. Okay. So these will be included. Hi students, welcome back. Let me continue with the subject theory of computation. So in this video, I want to explain you what are the different applications and what are the different types of automators. Let's see the applications. So the theory of computation plays an important role in the compiler design. Okay. So it is one of the important role that is going to be played in the compiler design, the theory of computation. In switching theory, if you take the switching theory and design and analysis of the digital circuits, automator theory is applied. So in those subjects also, here what are the applications here means in which fields we are using this theory of computation. So you get it out. We are studying about the symbols, transition diagrams, and the transition states and the functions. Where we use all those things. Okay, is it necessary students, welcome back. Coming to the next topic in theory of computations is deterministic finite automata. So this is one of the important concepts, the deterministic, non-deterministic. So in the previous video I explained there are different types of finite automata. The finite automata with output and without output. So the without output finite automatas are DFA, NDFA and epsilon with NDFA. And whereas with output are Millet machine and Moore machine. So now let's see the deterministic finite automata without an output. It's a finite automata with an output. Without output. Okay, remember that. The finite automata are called deterministic finite automata if the machine is read an input string one symbol at a time. So remember that this is a main difference between the finite automata and non-deterministic finite automata. Okay, so here DFA is going to read the input symbol, that is the input string, one symbol at a time. Suppose if it is reading A means it will read only one input string at a time, and B means it can read only B input string one symbol, that is one symbol at a time it can read. Okay, so there is no multiple paths, only the fixed path. Deterministic means fixed, only one way is there. Okay, it's a one way solution, either it has to be accepted or it has to be rejected. One thing, that is it has to be accepted or it has to be rejected. There is no alternate solution in the deterministic finite automata. Deterministic refers to the uniqueness of the computation. So that's what I said now. It is an uniqueness of the computation. In DFA, there is only one path. Containing multiple finite DFA cannot change state without any input character. Whenever the input character either 0 or 1 or A or B, anything. Okay, if any input character is present, then only it moves to the next state. DFA can, whenever the input character either 0 or 1, or this is one thing, here you have to remember that DFA can have multiple final states, that is either 1 or more. Here in this example, I have taken only one final state. So in DFA, there are multiple final states. And it is used in lexical analyzer and compiler. So where the DFA will be used? The DFA will be used in the lexical analysis in the compiler. In the compiler, the first phase is and delta is a transition function. So where the transition function is defined as delta is q into sigma is tends to q, means the state with input symbol leads to the next state. Current state, input symbol gives the next state. Okay, current state in input symbol leads to the next state. That is the definition of the transition function. Now let's see the graphical representation of DFA. So the DFA can be represented by diagrams called state diagram. So whatever you have seen, this is a state diagram. It's a digraph, means a directed graph. A direction should be there from which state to which state, what state it is going on what input. So the state is represented by a vertices. So here each state is represented by a vertices, like Q0, Q1, Q3, or A, B, C, D, anything. A state is represented by vertices. The arc labeled with an input character shown the transition. So here the arc which is labeled with an input character, this is an arc, okay, labeled with an input character which is showing, you call it as a transition. That's a transition. The arc labeled with an input character shows the transition. The initial state is marked with an arrow and the final state is denoted by the double circle. Initial state is marked with an arrow, and the final state will be with a double circle. So this is a graphical representation of the diagrams. Okay. So before going to the examples of this DFE, let me tell you what is an acceptance of a language. When you say the language, whatever the language that we are taking, that is accepted or rejected. I want to DFE, state will be with a double circle. So this is a graphical representation of the arrow, and the final state is denoted transition. Dark label with the input character shows a transition. The initial state is marked with an arrow, and the final reaching the final state F by taking the string W. So whenever I had taken one string, whether something A, B, A, C like this, so whenever if it reaches the final state, then the string is accepted. Otherwise, the string is rejected. Not accepted means if not reaching the final state. You have to remember that whenever the state reaches the final state, whenever the string reaches the final state, then you can say it is accepted. Otherwise, not accepted means not reaching the final state. So let me take the example. Suppose if the language with phi means there is no string is there, only one state is there, Q0, there is no next state. And if the language with an epsilon empty state, it is an initial state and it is a final state. Because there is no moves here, there is no moves, epsilon, there is no moves means no transition means it is the initial state as well as it is a final state. Suppose DFA to accept A. I want to construct a deterministic finite automator which accept A. Which accept A means whenever first you need to check what is the length of the string that I have taken. Here the states, how many states I need to be taken, you'll get it out how I'm going to construct the DFA diagram. Okay. First thing, whatever the input they are given, the minimum string you have to take it. It has to accept A. Means this is a condition. Here the minimum length of the minimum string length is 1. Okay. So the number of states will be depends on the minimum length of minimum string plus 1. Represents the number of states. So here the minimum string length is 1. 1 plus 1, 2. That means 2 states are required. Q0, Q1. So the Q0 on A goes to Q1, which is the final state. So here this is a DFA which accepts the string A. The accepts 0 or it has to accept more number of A's. More number 0 means epsilon. Epsilon moves means the string itself, you call it as an epsilon. A move that is taking place itself is epsilon. More A, so on like this. So the DFA for this is the initial state with the accept 0 and this is the final state which is having a loop. So it gives epsilon moves A like this. So this is about the acceptance of language. Now I hope you understand what exactly the DFA. So in the next videos I'll explain some more examples on how Friends, welcome back. Now let's see different examples of DFA, deterministic finite automata. So in this video, I'll explain some of examples. Means the question in the exam they are given in different ways. Okay, so don't confuse whenever they are given a question in different way, whatever you didn't understand. So try to elaborate the question. If you know the concept, whatever the way the question is given, you can able to write that answer. You will get the solution for that answer. Okay, so I'm going to tell that first. Thoroughly read the concept of the deterministic finite automata. Then come to the examples. Then you can understand whatever the question they are given. So let me take the first example. Now here, sometimes they'll give the direct way. Means they'll give all the inputs. You ask to find out some solution for that like this. So let's take example 1. Let the deterministic finite automata they are given as a B. It's a phi tuple A, B, C. Okay, it's a Q is a with having the 3 states. A, B, C are the 3 states. And the set is in between 0 and 1. Okay, this is the input symbols and these are the states. 3 states are there and the input symbol is 0, 1. And they are given directly, they are giving as a initial state is A. And they're also saying that the final state is C. And what they are asking? They are asking the transition function of the table is also given. We need to construct the state transition diagram for that. So the present state, they are given a table. So input 0 and 1. So initial state starts. What is the initial state? A is the initial state, right? So A on 0 they are given as A, B, and next state is B, C, A, and the final state is represented with star or double circle B, C. So they are given a transition table. Now by seeing this table, you can easily construct the DFA for this table. So you have to remember that in DFA, only one path which is going to that particular input. If you are taking any particular input, only one path will be going to that particular input. Okay, so the A can be right. So A on 0 they are given as A, B, and next state is B, C, A, and the final state is represented with star or double circle B, C. So they are given a transition table. Now by seeing this table, you can easily construct the DFA for this table. So you have to remember that in DFA, only one path which is going to that particular input. If you are taking any particular input, only one path will be going to that particular input. Okay, so the A can be on 0 it goes to only A, or it can on 1 it goes to only on to B. So here let me draw the diagram. What the initial state is A. So A on 0 it goes to A only. A on 1 it goes to B. Now coming to B. B on 0 goes to C. So B on 0 goes to C. B on 1 goes to A. B on 1 goes to A. Okay, B on 1 goes to A. Now coming to C. C is the final state. And C on 0 goes to B. So C on 0 goes to B. And C on 1 goes to C itself. So this is a state transition diagram for the given table. Okay, this is one way of asking the question. So let me take another way. So I'll try to cover almost all the types, means the different ways they are asking the question, because every student is getting confused. What is this question? What I have to draw and what I have to be implemented. So the same pattern means you can easily recognize, but let's see the different patterns. Let me take another example too. It's the another way of asking the question. So here they are giving the question like design DFA. I need to design DFA with they are given sigma 0, 1. A sigma means set of alphabet, means the input symbols are 0, 1, and it has to accept this input symbol accepts those string which starts with 1 and ends with 0. So they are asking that the set of string will be there. That string starts with 1 and ends with 0. So compulsory it has the language whatever we are taken. That string has to start with 1 and ends with 0. Starts with 1 and ends with 0. So the minimum length of the string here is 2. Okay. So the minimum length of the string is 2. It's a minimum length. Or else you can start with 1 or ends with 0. Starts with 1 and ends with 0. Starts with 1 or ends with 0. Means like this. So it should be anything. The length of the string they are not given the maximum length, but the minimum length is 2 compulsory, because the string should start with 1 and ends with 0. Means the two characters are there, two symbols are there. So the minimum length of the string is 2. So whenever the minimum length of the string is 2 is the number of states that are participating in the diagram is minimum length plus 1. So what is the minimum length? 2 plus 1, that is 3. So number of states are 3. So let's take 3 states. Okay. So now I want to construct the DFA, or the deterministic finite automator, with these inputs, and that string starts with 1 and ends with 0. So here this is the initial state. Let's take Q0, Q1 and Q2. So 3 states I have taken. Let's take first minimum string. The starting string starts with 1 and ends with 0. Starts with 1. So Q on 1 goes to Q1, and next it has to this Q2 is the final state on 0 goes to Q2. So the first string is accepted. Q on 1 leads to Q1, and Q1 on 0 goes to Q2. So 1 0. So the 1 0 it reaches the final state, means it accepted. Let's take suppose let me take this second. 1 0 0. Is it accepted or not? I have to check. So Q0 on 1 goes to Q1. So let me take 100. So Q0 1. Next Q0 on 0 0, and again the 0 has to become. Let's take this loop. So now this is also accepted. So Q0 on 1 1 0 0. It reaching the final thing is we have to reach the final state. Okay. So next let me take this string 1 0 1 0. Our question is starts with 1 ends with 0. So here I starts with 1 and I ends with 0. So in between whatever it may be. Let's check. Q0 on 1 goes to Q1. Q1 on 0 goes to Q2. So again Q2 on 0 goes to Q2 itself. Means it is reaching the final state. Accepted. So this time let me take 1 0 1 0 1 0 0. Let me check this. Is it accepted or not? Means in this way you need to be checked. So Q0 on 1 goes to Q1, 0, Q2, Q2 on 1. So again it has to come like this. Q2 on 1 goes to Q1, and Q1 on 0 goes to 0, like this. So like this we have to be checked. So here, how I'm going to construct the DFA? The DFA means each state has to go either 1 and the 0. So here it is going to 1. And here the Q1 is going to 0 and it should be 1. The starts with 1. Okay, don't disturb Q0. Q0 is always starts with 1. So it is not starting with 0. Starting with 0 means you have to take a loop here. But the thing is, question starts with 1 means Q0 is having only one input 1. It doesn't have the 0. But Q1 is having the 0 as well as the 1. Okay, means in between this, anything will be there. And Q2 should be 0 and it can goes to 1. And finally it has to reach the 0. Our aim is ends with 0. So the loop should be in the final state is 0. And here it starts with 1 means it is going to 1 to the next state as a 1. It doesn't have any loop. So this is the DFA for the given question. So I think you're a little bit confused. So let me take some more examples. So try until you clear your confusion. Okay, here the main thing is, what is the question they are given? Starts with 1. So I started the state with 1 and I started the state ends with 0. So don't disturb these two and check the remaining intermediate state. This state has to go to 1 as well as the 0 because the input strings are 0 and 1. So it is going to 0 and within loop it is 1. And this Q2 is also going to 0 and it is going to 1. Okay, at the same time it is having this loop because it has to end with the 0. Thank you. Hi students, so let's continue with the example. Let me explain you with the example 3, DFA. So let's design a finite automator, that is a deterministic finite automator with the input symbol they are given as 0 and 1, and it has given the condition as accepts even number of zeros and even number of ones. So this is a question. So even number of zeros and even number of ones should be accepted. So the finite automator will consider 4 different stages. So even number of zeros means what's the minimum state? Minimum, let the language is what's the minimum. Even number of zeros should be there and even number of ones should be there. So means total how much? The total zero, even number of zeros, and either it has should be even number of ones. So it should be 0 0 or 1 1 0 or 1 0 0. 1 1 0. So like this means it should be have even number of zeros or it should be have even number of ones should be there. So here in this condition it is only even number of zeros are there and even number of ones are there. So like this it will be there. I need to construct a DFA with this input and which that accepts even number of zeros and it accepts even number of ones. Let me construct the diagram. So here how many states will be there? Either it can accept even number of zeros and along the input string is 0 and 1. So 0 and 1 should be compulsory. And the condition is even number of zeros should be either it should be 0 even number of zeros or it should be even number of ones are there. So total the length is minimum is 3. So 3 plus 1 4. So total number of states are 4 should be there. So Q0, Q1, Q2, Q3. So I have taken 4 states. Okay, so it should be even number of 1 starts with Q0. Let's take the initial states start with Q0. Let's take even number of zeros. So Q0 on 0 goes to Q1, Q0 on 1 goes to Q2, Q2 on 0 goes to Q3 and 1. So did you check here? So here what you get? You'll get a Q0. Suppose if you take Q0 as initial state, the state of even number of, so it should be even number of 1 starts with Q0. Let's take the initial states start with Q0. Let's take even number of zeros. Even number of zeros, and either it has should be even number of ones. So it should be 0 0 or 1 1 0 or 1 0 0 1 1 0. So like this means it should be have even number of zeros or it should be have even number of ones should be there. So here in this condition it is only even number of zeros are there and even number of ones are there. So like this it will be there. I need to construct a DFA with this input and which that accepts even number of zeros and it accepts even number of ones. Let me construct the diagram. So here how many states will be there? Either it can accept even number of zeros and along the input string is 0 and 1. So 0 and 1 should be compulsory. And the condition is even number of zeros should be either it should be 0 even number of zeros or it should be even number of ones are there. So total the length is minimum is 3. So 3 plus 1 4. So total number of states are 4 should be there. So Q0. So Q0 on 0 goes to Q1. Q0 on 1 goes to Q2. Q2 on 0 goes to Q3 and 1. So did you check here? So here what you get? You'll get a Q0. Suppose if you take Q0 as initial state, the state Q3. So I have taken 4 states. Okay, so it should be even number of 1 starts with Q0. Let's take the initial states start with Q0. Let's take even number of zeros. So Q0 on 0 goes to Q1. Q0 on 1 goes to Q2. Q2 on 0 goes to Q3 and 1. So did you check here? So here what you get? You'll get a Q0. Suppose if you take Q0 as initial state, the state of even number of zeros and even number of ones. So state if I take input 0, okay, so I have taken input 0, it is going even number of zeros and even number of ones. Suppose if I take input 1, so this time I'm taking input 1 0 1 and 0. So here in this state also, if I take the input as a 1, I'm getting even number of ones and even number of zeros. That means this is the final state, initial state as well as the final state. So whatever the string you have taken here means if this condition has satisfied even number of zeros and the even number of ones means this is the 0. So first I had taken the 0 and I reaching I have to take 0 as well as a 1 in the deterministic finite automator. So that is leads to only one path. If 0 is going to another means the 1 should be goes to another state. Okay, to the next state. Next if you take Q1, let's take Q1. This Q1 is having how many the state of odd number of zeros should be there. Okay, odd number of zeros Q1. So if I take this here, it's going 1 0 1. So I have to reach the final state. So here 2 ones are there and 1 0 means. So the Q1 is state of odd number of zeros, only one zero is there, and even number of ones. Now state Q2. Q2, check this. So either you can go this side or this side. So if you go this side, you're getting only 1 0 and 1 to reach to the final state. So Q2 is state of odd number of zeros as well as odd number of ones. Suppose if you take Q3, I'll go this side. 0, 1, 0. Okay, so 0, 1, 0. That means Q3 has even number of zeros and odd number of ones. So this is accepted. Okay, if I want the complete even number of zeros and even number of ones, the Q0 should be like this. So it is the initial as well as the final state. So which this state, so we have to accept the strings which consisting of even number of zeros and even number of ones only. So only those strings will be accepted and others will be rejected. Thank you. Hi students, let's continue with the DFA examples. So why I'm telling so many of examples means the more the examples you can try, you'll get the concept of DFA. So here they're asking the question like construct DFA accepting all strings over AB. So each state has to go for one particular path A and B, and the string should end with AB. So here they're saying that whatever the language I taken, that string should end with AB. Ending should be AB. So AB means the minimum length of the string is 2. Ending with is AB. Starting with inside. So ending with AB or AB. So like this, whatever it may be, whatever the string you are taking, the ending should be AB. So what is the minimum length here? The minimum length is 2. So number of states are participating in the DFA, or the number of states is equal to 2 plus 1, 3 states are there. Okay, so let me take Q0. Q0, Q1 and Q2. Okay, so first take the minimum length. This is the initial state, and let me take this the final state. Why I'm taking this final statement? See here. So if you take minimum length, Q0 on A goes to Q1 and Q0 on B goes to Q2. So the AB string is accepted because it has to reach the final state. So Q0 on A goes to Q1, which is the transition function next state. Q1 on B, transition function leads to final state Q2. So AB is accepted. Okay, so Q0, the string should start with the, they didn't say the string has starts with either A or B. It doesn't say anything. So it can be start with A or it can start with the B. Okay, so the Q0 can start with A, that is also true, and the Q0 can start with B, this is also true. So because it is B, so BAB is accepted. Okay, AB is also accepted. So now coming to the Q1. So the Q1 is first, it's going to the B, and next input is A should be there. So the final is it has to reach to the B, BA, and the ending of the string should be A only. So BAAB. So this is also accepted because the ending should be AB. So Q1 is over. Now coming to the Q2. So Q2, the string should end with AB. So A. If I take this, if I take Q2 on A, it goes to A. On Q1 A, it goes to A, A, B. So A, B. So this is also accepted. So that's why I have taken the input A. Next, the input on B. So Q2 on B, 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 A, B. Okay, means whatever the intermediate you are taking, the final should be end with AB. So that's why I constructed this DFA. You will get it out now. How you understand? How can I know that I have go to A like this and I have go to B for here only, not here? Because in the DFA there is a rule, only one part should be there for one state. So for one state it has to go only one input A. Okay, here you can't go, the B cannot goes to here. Okay, suppose if I take the B loop here, I'll get BB. So the BB string is not accepted. Suppose if I take in something like here, you'll get it. Suppose if I take here, this is wrong because BAABB. The string will ends with the BB, but it is wrong. So that's why I have taken the loop to here. I can't take to here because already Q2 is going to next state on A to Q1. So next in the DFA I have to choose another state on that another